talking about operads. I think it's operad, properads, and more, right, Martin?
All right.
Thank you.
Okay, so I'm very happy. All right. Usually I say that I'm very happy that I've been invited to some place and then I can see a new, beautiful locations, towns, meet people. Well, in that strange situation, I am in Prague, and I'm not happy that I'm here because I was looking forward to be in Barcelona. Actually, I intended to move in with my car for this one semester. But okay, what can be done? Maybe some of yours may wonder why I am so well dressed. So it is because I knew that Ike was going to talk before me, and he is usually dressed up. So I didn't want to be shamed by him. Well, and I think that I may start my talk. So the purpose of my talk is to give you some clue how to get around the complicated world of operads, properads, and similar structures. Well, as a first approximation of what these things may be. Okay, so let me try to move to the other board. And I have to say that this is my absolutely first online talk, so I have no idea how it would work out. So, but anyway, so operads. So can you read this? It's readable?
Perfect. It's absolutely perfect.
Perfect. Okay, so operads are maybe thought as abstractions of families of maps. Let's say maps with several inputs and one output. So abstraction of families of maps of this type and their composition. So this is what, let's say, operads may be thought as. And props, which is, by the way, abbreviation for product and permutation category, may be thought as abstractions of families of maps with several inputs and several outputs. Although, as we will see later on, it is not true literally, because they are other structures which are such that you cannot actually distinguish between inputs and outputs, such as module operads or cyclic operads, and they are even more exotic structures like Batanians and operads and hyperoperads, permutations, and so on, which I will try to mention in my talk as well. So let me draw a table of operad-like structures. Let me call the first column by directed structures. So these are structures where I may distinguish between inputs and the outputs. So they are certainly, okay, I mean that I know what the outputs are and what the inputs are. So I always draw my pictures from bottom up. So certainly here I have operads, props, properads, half props, I'm going to mention all these structures at least in passing, and then they are non-directed. Structures. namely cyclic operads and modular operads. And then there is a one particle example of structure which somehow lies in between these two things, and these are wheel props. Wheel props. And there are some other structures which doesn't exactly fit into the scheme, like hyperoperads and operads, permudads, and so on. So is it still readable? Okay.
Yes, yes, it's great.
So for me, operad-like or prop-like structures are characterized, or at least from the point of view of this talk, by class of graphs which describe the way the abstracts of operations are composed. And these graphs I will call pasting schemes, or another possible names will be flow diagram, which people in computer science would probably use. And these classes of graphs must satisfy some condition which I call hereditarity condition, and I will specify it later on as well. So maybe I may mention also a couple of other approaches how to generalize operads. There is a approach by Borisov and Manin, which was kind of generalized later on by Kaufman and Ward, and it got name of Feynman categories, which is actually kind of equivalent to the approach based on colored operads. Let me mention also other generalizations like moment categories by Clemens Berger, polynomial monads by, let's say, Batanin and Koch, although I'm sure that I've forgotten to name some other important people. I'm sorry for that. They are operator categories by Barwick, and they are finally operatic categories which are introduced with Markl Batanin. So let me in particular put the name of these last two things on the board. So this is operator categories by Clark Barwick, and opera categories by Markl Batanin and me. And what they have in common, that very important role is played by the notion of fibers. So this approach, these two last approaches emphasize the role of the fibers, and I will, at the end of my talk, indicate what these operatic categories are. And I have to say that all the structures which I mentioned above can be described within the framework of operatic categories. All right, so I believe it should be enough for the introduction. And now let's move to particle examples of operads, and let me try to focus on the other board. Yeah, seems to be working. So I'm going to use two kinds of definition. So the first is the unbiased type of definition, and the other one is biased. Again, this terminology is not due to me. I got it from Lester, and I believe it will become clear what I mean by unbiased and by biased. So unbiased for me means more or less the same as monadic. Definition. So let me just very briefly recall what the monad is, but I'm not going to go into any detail, and I have to say that I'm going to ignore most of subtleties and details, which are sometimes important during my talk, because indeed I just want to give you some ideas. So I would say that monad, also called a triple in Montreal. So monad is a functor which is living on a category C. So it is a functor from C to C, together with two transformation, with this transformation mu, which goes from T square into T, and we may think of it as a kind of multiplication. And there is also a unit transformation which goes from identity functor into T. And these operations should have a property that together with these two operations, the functor is unital associative monoid in endofunctors of C. So having a monad, I may speak about algebra. So algebra over T, okay, let me use another chalk, is a morphism. So first of all, it is a object of C, which is equipped with a morphism alpha from TA into A that satisfies some associativity and unitality property, which I'm not going to mention because it will take me far away from the purpose of my talk. Let me instead give you an example of such a monad. So yeah, I think that you can still see it. This is a free monoid monad. Free monoid monad. The category C in this case is a category of sets. And how T is defined. So T on X is a disjoint union of Cartesian products of X. And how I may think of element of X power n, I may think this is certainly a n tuple of elements from X, but I like to visualize them as a kind of string, x1, x2, xn. And this is also going to be the first example of what I would call pasting diagram. So pasting diagram in that case is just a line or a couple of intervals. And how I may think of T squared X. So this is a free, this kind of thing where instead of X, I have Tx. So again, I may visualize, and I'll draw it horizontally because I don't have enough room on the board. I can visualize this as a nested intervals of dots. So this may be the example. So these intervals, they indicate that here I am in Tx, and the thing then it symbolizes element of T square X, and how mu in this particle case works, it just forgets the bracketings. So I believe it's pretty obvious, and certainly you are immediately able to see how the unit is defined.
Martin, I'm sorry. If you want the free monoid, you want n to start at 0, or you want the free non-unital monoid?
Free non-unital unit.
Okay, sorry.
Yeah, free. Oh, okay. I say I'm going to actually put all these details on the carpet. So whenever I speak about operads, I'm not going to say they have a pi 0 or pi 1, you know, just, but you are, of course, absolutely right that if I want to have unique, I have to at one point set my favorite 1 point set. All right, very good. So it's probably not very surprising when I say that the algebra over this monad, so T algebra, is a okay associative, well, non-unital monoid. And in fact, the Tx is precisely the free monoid generated by X. And this is a general case thanks to theorem by Allenbank and Moore, which says that practically each monad is a monad of free algebras in the category of algebras which is determined by this monad. But I'm not going to delve into this thoroughly anymore. So this is what I would call unbiased definition. Unbiased for me means that all the operations are packed together and all the axioms are built in the definition of monad. Again, this is not my invention. I got it from Lester, this kind of definition or this kind of distinction. And what is a biased definition? Biased definition of a monoid, non-unital monoid, is a set X, fine, and a binary operation from X to X into X. So now I have just one operation, so definition is biased towards binary operations, and it must be associative. So it's the same as. Okay, so typical feature of biased definition is that I have, well, usually, but not always, finite or countable number of operations and finite or countable number of axioms. And I will follow the scheme in the rest of my talk as well. Yeah. So, very good. So what about operads? I mean, a very, very classical operads. So what is the unbiased definition? I have to say what category C is. So category C is a category of collections. Yeah, by collection, I mean collection of vector spaces, topological spaces, simply for sets, simply elements of some monoidal, symmetric monoidal category. And well, just to put something on the board, I put one here, but I'm very flexible where the collection starts. And then there are, as always, two versions. There is a symmetric version where these spaces are sigma and modules, or the non-symmetric where they are just, well, nothing, okay, no action. So the classical operads should generalize the composition of, as I put on the first board, it's still there, but you cannot see it, composition of functions with several inputs and one output. So how this composition may look, okay, I may do this to it. I may do this kind of composition, and I may go on, and I would find that the pasting scheme is are rooted, which is the same as directed trees, which are planar in case of non-symmetric operads. So if I wish to be slightly more precise, I would say that the monad that describes it, again, it has to belong to this category, so it must be collection. So I must say what is nth component of this monad. And this is it is a set or vector space depending on in which category I am working. which contains or consists of rooted trees whose vertices are decorated by elements of my collection. So this fellow is decorated by something from X2. This fellow is decorated from something from X3. Yeah. And what is this N? This N is the number of incoming edges. So this is how a triple of rooted trees looks. T square then consists of rooted trees whose vertices are decorated by decorated rooted trees. And mu, the multiplication, is the functor that forgets the nests, or it forgets the nesting. Okay. So this is unbiased definition of ordinary operads. And what is definition? What is this biased definition? Let me erase the board. We actually have the third column of boards in the room, but the camera is probably not flexible enough to move to the third. Oh yeah. Oh yeah. Wow, it will be kind of distorted. But
good.
Well, we'll try and we'll try.
And, too much.
It's too sensitive.
It is.
Okay, now it's all right. So what I was saying. Okay, so what is the bias definition of ordinary operads? So what are the generating operations? The generating operations are circle I. Now they are called partial composition or circle I operations, which go from xm. Well, I write tensor product, but I mean the manual structure in the underlying category, xn, and they go to xm plus n minus 1. And I may think of them as symbolizing or being connected to this very particle type of a planar tree, where this is the input of the 8th input of the first operation, and I have m inputs on the first operation. This is this m, and I have n inputs of the second operation. This is the second n, and of course the total number of inputs is m plus n minus 1, and some associativity and unitarity must be satisfied, but again, I'm not going to specify it. Let me just make one kind of important remark. So there is another point of view to operads, which is actually attributed to Peter May, but in fact, I think it has to be attributed to Boardman and Vogt. Yeah, which defines the operad not by using these partial operations, but where I have operations, generating operations of this type. So all the inputs of the upper operations are taken care of at once. And it turns out that under, for instance, the presence of unit, the definitions are the same. They are examples of, natural examples where units are not present and these definitions differ. And I have to say that I don't have any nice simple description of pasting diagrams for May's operad. In one of my papers, probably in several of them, I said that it is trees with levels, but it is not tree. It is not true. I can describe it in kind of inductive way, but I don't have any kind of nice description. So Well, I may explain a little bit more about it if you are interested, but somehow, from many reasons, this definition is much better. And actually, the way I introduced it was because it's binary. So if you have 3 operads, for instance, they are naturally graded by number of operations, which is not true for this type of operads. Very good. So what about this magic hereditary property? So you already saw examples of pasting schemes. So the pasting scheme is a class of graphs. But not every pasting scheme can be used to define operads. Okay, it moved. Board move, I don't know why. Well, at least something you can see. All right. Okay, so what is hereditarity means? So as I say, not every class of graphs can be used to define operads. It says roughly the following thing. Assume you have a graph in this class. So this is graph in my class. Or something like this. And suppose that the vertices of the graph of the graph are itself graphs of the same class. It's kind of difficult to draw it, but I'll try. So the vertices themselves are, so the graph is nested. This is what I want to say. So the vertex itself is a graph, something like this. So I'm given a graph whose vertices are decorated by graphs of the same class. And hereditarity means that if I remove the nests, so if I forget these little things, I will get graph of the same class. So probably the best way how to explain it is to give the following very stupid example of class of graphs which are not hereditary. So graphs with 2 vertices. Yeah, so I mean, why it is not hereditary? Suppose that I have something like this, and it has another vertex. I mean, it's kind of obvious if you start thinking about it, which is again a graph with precisely 2 vertices. Okay, so this is this little graph. Both are from the class, but if you remove it, you'll get graph with 3 vertices. So obviously the hereditarity is violated. And it's kind of interesting to try to figure out why I need this property, why this this kind of graphs wouldn't lead to any interesting definition or sensible definition. Okay. So another example, I hope that I may still use this board. So another example are cyclic operads. So why else? I said that ordinary operads are abstractions of operations with several inputs and one output. cyclic operads are beasts for which I cannot distinguish between the inputs and outputs. So I wish to think of them rather of kind of blobs, which, I don't know, unify things. So maybe something which is very close to these idea are vertex operators from physics. So pasting schemes are any trees, any connected trees, I have to say. Connected trees. Well, otherwise I would say forest. So by tree I mean connected tree, of course. So this is a example of such a connected, well, such abstract tree. So I have no direction. I cannot distinguish between the outputs and inputs of vertices. So this is a pasting scheme for cyclic operads. And what is bias definition? It's given by, okay, I'll draw the graph which corresponds to the operations. So it is the graph with one internal edge, and it has this edge has a label I. Let's say this has a label J, and the operation which is related to this is something which I think I denoted by circle ij, which goes from xm times xn into xm plus n minus 2. Okay, so this is bias definition of operations that appear in bias definition of cyclic operads, and again some associativity has to be satisfied. So by the way, there are two versions of cyclic operads. The one which is, let's say, the most classical one is the definition where these things are acted on by symmetry groups on M elements. And there is also non-symmetric version where this fellow is acted on by cyclic group. I don't know what is your favorite notation for cyclic group on M elements. So just rotations. Okay, and now there is no way but to erase the board. Možná tím nějak pověřím, kde seš. Okay. So by the way, how is the weather in Barcelona? It's warm, or?
It's fine, thank you.
It's weather, but still not good enough.
Okay, so let's continue. Yeah. Very good. So probably the most complex example is example of modular operads. So here the pasting schemes are connected graphs. which are moreover decorated, So what is decoration? Decoration is a map from set of vertices of gamma into natural number, while 0 is natural number as well in this context. I may also call it a marking. And this decoration is abstraction of genus because it has some geometric origin where G was indeed a genus. And fine, so if I'm given such a decorated graph, I define, so this is a genus of vertices, I may as well define genus of graph gamma as sum of these local genera GV, where V goes over vertices, plus the first Betty number of gamma, which is the dimension of H1 of geometric realization of gamma. So this is a genus. And what is the underlying category for model operads? So underlying category are modular collections. So what is a modular collection? I'll try to list it a little bit. Modular collection is something which is parameterized by natural number n, as in case of operads, and also by a genus G. So n and G are natural numbers. And what is the pasting scheme, or what is the triple or monad that describes it? So as I say, the pasting schemes are decorated graphs. So it may be something like this. Well, I may have a loops. In fact, it may be anything. So by the way, the loops here, they bring a lot of problems because it means that there are a lot of automorphisms of the pasting scheme. So it behaves rather as an orbifold or stuck in a sense, which makes it quite nasty, any kind of calculation with this and colimits and so on. Anyway, so it is not important. And what about decoration of vertices? So this is a marked or labeled graph. So let's say that this fellow is labeled, so this is a V. So let's say that GV is what is your favorite number? 5, okay, is 5. So then this vertex will be decorated by something which is in X 1, 2, 3, 4, 5. Okay, 5. And the genus is 5 as well, so it's likely dual number in this case. Okay, so this is unbiased definition. You can figure out the axioms actually. And what is biased definition of modular operads? So again, I draw the lithographs which are beyond the definition, the operations. So let's say this has a genus G1. It has a genus G2. It has a label I. It has a label J. And let's say that it has a M inputs and has a N inputs. Again, I say inputs, but I cannot speak about inputs and outputs, so maybe better would be to say adjacent edges. And the corresponding operation which generates the bias definition is again circle ij, as in case of model of cyclic operads. But in this case, I also have to say what it does with a genus. So it goes like this, X, M, so N, let's n G2, and it's additive with respect to the genus, which is again taken from geometric motivations, n plus n minus 2, and the genus is G1 plus G2. Yeah, but since, as I believe it's still on the board, I may also have loops, so I have another operation on top of the ones which I saw in case of cyclic operads, namely operation which is related to a graph like this. Okay. So let's say that the genus of the vertex is G. Let's say that the label of this, well, adjacent edge or half edge is I, of this is J. Then I have a contraction I, J, which goes from X, M, G into X. So it takes two adjacent edges away. So M minus 2. And again, out of geometric motivations, it raises genus by 1. So this is these are operations for unbiased definition of module operad. And as I say, everything is very heavily motivated by geometry. So there is a notion of stability which was taken by analyzing case of stable curves. I'll present very short and simplified definition. So I say that couple NG of natural numbers is unstable or not stable. So unstable. So I take this negativistic definition. So it's not stable, it's unstable if NG and G is either 0, 0, or 1, 0, or 2, 0, or 0 and 1. So by the way, this means a sphere or Riemann surface of genus 0 without any puncture. This is one puncture, this is two punctures. So sphere is stable, meaning that it has only discrete group of automorphism. If it has 3 marked points or more, and this is a torus. So torus with 1 marked point is not stable. Yeah. Right. Okay. So this is unstable. Any other couples are stable by definition. And what is stable graph? So stable graph. So it has some number of legs. So these are these external half edges. So stable graph gamma is stable if the couple consisting of number of legs of gamma and the genus which was defined above, I guess, yeah, is stable. Yeah. And while to verify that all previous examples of graphs or classes of graphs were hereditary, here you need to use some elementary properties of Betti numbers to prove that indeed the class of stable graphs is hereditary. And now I need to erase another board. And actually now I realize the basic difference between talks given to live audience and online talk, because when I erase the board, I usually ask some question to the the people in the classroom, but I cannot. I ask what is the weather in Barcelona and so on. I have to turn the mic on, so it has some special feature, this kind of lecturing.
But of course you can ask if you want.
We are still here, you know.
Okay. Yeah. I have another 30 minutes, so it's all right. And another feature is that I have a couple of people here in this room, and of course I wish to look at their faces, but I have to check if the board is visible. So maybe one can get used to it, but for me it's complete.
Well, we have had that here for people being teaching in rooms that were also broadcasted for students that were confined, and it's not easy because you have to cater at the same time for the pupils which are in the room and for the ones which are at their homes.
All right.
But we should not get used to this.
So
No,
we should not get used to that anyway. We should go back to real life.
it was not done on a voluntary basis, I can tell you.
very good. So where we are, 9. So fine. So basically, this was all about the opera type of objects. So what about prop type of objects? So as I say, the abstract family of maps from with m inputs and n outputs. So you see that, for instance, if I'm in category of topological spaces or in any Cartesian category, all these maps are given by projections. Therefore, I will not get anything new in this setup, which is the case of the Bormann and Vogt approach, which actually is equivalent to using Operads precisely because they are working in Cartesian category. Therefore, speaking about props meaningfully means to be in a, let's say, category of vector spaces or chain complexes or something like this. But anyway, so what is a prop? Prop is a collection. Prop is a collection P, M, N. Again, I write M and N like this, but I'll be very fussy about it later on. And I shall think about it as of something which generalizes the set or space of linear maps from V times M into V times N. So what I can do with these maps, I can put one such a map on the top of another one, which is, well, let's call it vertical composition, P, M, N times P, N, K, and it takes me into P, M, K, and the picture is going to be, okay, so I have operation with okay, now I'm drawing it from the bottom up, so I have picture with M inputs. Here I have N outputs, and the fellow above it has also N inputs, and the number of outputs is K. So what I get if I compose, I'll get mapped with M inputs and K outputs. So this is vertical composition. And there's also a horizontal composition which generalizes operation of pot into maps side by side. So again, if I have a map, yeah, I am not going to draw the arrows to speed things up. So I have let's say M1 inputs and M2 inputs. I have N1 output, M2 and N2 outputs, and the result is something which has M1 plus M2 inputs and N1 plus N2 outputs. And this is a horizontal composition which goes, let me denote it in this way, it goes from P M1 and 1 times P M2 M2 into P, there is no room on the board, M2, comma, N1 plus N2. And there is also the action of symmetry group, and the axioms which it has to satisfy is can be read off all of them by analyzing this example. So this is the recipe to get bias definition of props. Notice that I kind of switched the order and I started with bias definition. So what is unbiased definition? What is a paste-in scheme for props? So paste-in schemes are are directed graphs So what is directed graph? First of all, I don't assume anything about connectivity or simply connectivity. And what is directed? It means that each edge has direction. And there are no directed loops. No directed loops. So I believe it's quite obvious. So they are graphs like this. Okay, something more fancy, I don't know. Graphs like this, but as I say, directed loops are not allowed. So actually, yeah, I may have non-directed loops. So this is I may have parallel edges. This is the point, but I may not have thing like, for instance, like this. So this is forbidden. So these are pasting schemes for props, but one has to be very careful. Actually, the statement that the monad that is based on this kind of graphs indeed describes three props is very complex. It's not simple one, and there is one subtlety which cost several people whom I know a couple of years of their lives, that the correspondence between this let's say monadic approach based on graphs and biased approach works only under the condition that P00 is P10 is P01. And why it is so? Because if I admit something in P00 as a pasting scheme, I may have such a graph. This is completely legitimate graph. And to this graph, I must have a map from P0 into P00. Very good, but which is which? So, I mean, which is left, which is right. I may freely move these things around, you know. So in order this to work, I need to have some ways to distinguish which vertex lies on the left from the other one on the right. So there is a notion of graphical props, which are props that are based on these pasting schemes, but one has to be careful that they are not the same as the props given, I think, by McLean, using this unbiased definition, basically.
Martin, your condition is that these p's are equal or they are all zero?
Yeah, I'm sorry. Yeah.
Okay, good. Thank you.
Simply there are no constant from, yeah, very good, thank you. Yeah, and I would say that in general props are not very nice objects, but there is a much nicer version which was introduced by Bruno. They are called properads. Yeah, and properad is a prop whose pasting scheme is based on connected graphs. Therefore, these pathological things are excluded. And I admit that all examples from nature which I know, which are over props, are in fact over properads. I can cook up very artificial example of structures which exist over props, not over properads, but you would probably never want to meet them. And okay, so I say what is unbiased definition, and what is biased definition, what are structure operations. So I just draw the picture because to invent notation for operations is not necessary at this stage. So the simple graphs that generate operations are, okay, so these are things with some number of outputs, some number of inputs. So some inputs are connected with the outputs of the other one, and there are some outputs and input which may go around. And this kind of operations generate the bias definition of properad. And again, what is nice is that it is generated by quadratic operations, although to write down the axioms will be a lot of headache. Můžeš zase, když tak přetočit na tuhle fajn, dobrý. So now I'm going to mention kind of exotic structure, which I call half prop, but it was before Bruno came up with the definition of properad. So nowadays I would call it half properad. I think it's a better name. So, but okay, this is the historical name, half prop. So what are pasting schemes of half props? So again, they are connected, simply connected, graphs. So So trees, but they are directed, so they are not suitable. But with the following property, which I again define in kind of negativistic way, such that now it's going to be tricky. Each edge of gamma is either the unique outgoing edge of its initial vertex, or so this is either or the unique ingoing of its terminal vertex. So example, this is perfectly all right. So this edge is the only outgoing edge of its initial vertex, but this is not all right anymore. This is forbidden. And why these half props are good for? There is okay, so everyone knows what the bialgebra is. Bialgebra is a structure with multiplication and co-multiplication, which are associative, co-associative, and they satisfy, basically they commute with each other in the following way, A delta B, and these are objects over properads. But if I, instead of this right-hand side, I just declare this to be 0, I will get structure which you probably won't find in nature, but which has a property that bialgebra, the axiom of bialgebras, is in a sense deformation or perturbation of the structure. And while the algebras over general props are very difficult to handle, by the way, the prop that describes this fellow is not quadratic in any thinkable sense. This is perfectly quadratic structure. I may use all tricks which I have been using most of my life and calculate minimum model of this fellow. And then I prove that the minimum model for bialgebra prop is a perturbation, which gave me a description of generators and also some insight to some lower dimensional, lower degree terms of this minimum model. So as I say, you probably won't find many structure in nature which leads over half props, but still they play some role. Okay, another 10 minutes. Yeah. So let me very, very briefly mention the operatic category stuff. So as I say, operatic category is approach to operads, which uses the notion of fiber. I'm not going to give you definition because I don't have a time, but I will at least indicate what is it and give you one example which doesn't fit to the previous examples in the sense that there is nothing like pasting scheme, at least not in an obvious way, which could be related with the example. So operatic category is, as the name suggests, a category O, such that, among other things, each morphism each morphism, what is my notation here? Each morphism from S into T has fibers. Let's say T1, Tk, fibers which are again objects of the category of this category, and they fulfill some properties. And having such a thing, I may define operad in O, or operad over O if you want, as a collection, So it will be collection which is indexed by objects of the category, and structure operations are the following: given map P with fibers T1 up to Tk, the structure operation is related to such a map is a map from AT. No, this is P. Okay, PT times P. Now I have my fibers P Tk into PS. So somehow from this kind of big thing, you may think of it as a kernel. So from the image and the kernels, you cook up something in the big thing. And example, you take O, skeletal category of finite numbers, or category of final ordinals if you want, and by fibers you take preimages, just ordinary preimages, and you will figure out that operads are just ordinary operads. If instead of finite sets you take delta, you'll get non-sigma, non-symmetric operads. But I wish to give you kind of more, well, I wouldn't say interesting, this is very interesting, but from the point of view of this menagerie of operads, kind of interesting example is example of n operads due to Markl-Batanin, where n is natural number. I will say only comment only on case of two operads where n is 2. So what is operary category in this case? It is category of 2 trees. So what is 2 tree? It's what is it? So I have K1, this is finite ordinal. Well, in fact, I think of it as a set 1 up to K2. I have order preserving map into K1, needn't be epimorphic. Well, and then I have terminal ordinal, which I don't need to specify. So this is a 2 tree. Why it is called 2 tree? Because example, okay, example. So K2 is just 3, 1, 2, 3, and K1, 2 points, 1, 2. So everything is labeled from the left to the right, and my map goes this way. So it maps 1 and 2 into 1 in K1 and 3 in 2 in K1. And that there is this terminal ordinal which brings no information in, but if I complete a picture, I'll see previous levels. And Markl defined maps of trees of this type in very nice but kind of technical manner, basically saying that the maps are these maps of trees which preserve the order of fibers. And he also defined the fibers. And again, I'm not going to detail, but I will give you example. So I draw another 2 tree. And I define a map. I define a map by saying that it says 1 and 2 here. No, I will do it even more complicated. 1 and 3 here into the first, whatever, leg, and 2 into the second. So it's well-defined map of trees. And I didn't say how fibers are defined, but they are defined in very nice and geometric way, namely such a map. So this is my P. It would have 2 fibers. They would sit over the branches, or how to call it. So the fiber over this fellow is everything which is mapped to the line or the path which connects this vertex with a root. So what goes there? So Stanley 1 and 3. I think this is it. So this is fiber over. I'll draw it a different way. Is it still visible? Maybe I'll use the. No,
that's okay. That's still okay.
It's okay. I'll erase something above it, so I'll get more room. All right. So this is the fiber. This is the first fiber. And what is fiber over 2? Again, everything which goes, I use different color, everything which goes to the path which connects the second stem with the root. So this is this. If I am not mistaken. So the second fiber is this. So notice that the branches needn't grow all the way up. The trees are not pruned, or what is the terminology? And what is structure operations? Operation which is related to this map. All right, so it should go from a small thing. So it goes from P. I'll be very brief. Times fibers. Again, actually, they are. Markl's operads are sensible only in Cartesian category. So I'll rather put just a cross than the product. Okay, times the second fiber, and the image must be in the big thing. So in this tree, and this is gamma. So these are the beasts called 2 operads, and why they are so important, because there is a famous, or at least in some circles, famous result saying that the space is a weak homotopy, depending on how precise you wish to be, if and only if it is acted on by contractible E and operad. And this offers one of several proofs of the Gaussian conjecture, for instance. You can prove that it is acted on by contractible 2 operad. So this is the end of a talk of how you put it, Middle Europe or Central Europe professor. So thank you for your attention.
Thank you very much for this very nice talk.
There is real applause. You cannot hear it, but there are some real people, not just robots.
There are real people in front of a blackboard. Wow.
Yeah. Thanks a lot, Martin, also for being able to adapt so quickly to the change of plans, and for doing such a nice talk. And also you cover everything I asked you to cover, which was a lot. So that is really, really nice.
Okay.
Do we have any questions? So feel free.
I have a very
Go on, Ike.
Simple question, yes, but you mentioned several times in your modular story that everything was geometrically motivated. Wouldn't it be nice to draw some surfaces which also explains the word modular?
Can you repeat the question? I mean, the sound is not very good. So,
could you draw some surfaces to illustrate the terminology and geometric motivation in your definition of modular operads?
You mean modular operads?
Yeah.
Okay, I
maybe nice for the audience.
Yeah. Okay, so this is one-dimensional complex curve. So to draw one-dimensional complex curve, stable curve is well, besides some very simple cases, okay, almost impossible. But the idea is the following: that so what is a stable curve? So stable curve is a complex curve that may have several components, but they intersect in very nice ways. So usually people draw the intersection like this, and the components may have a genus, and this thing form a modular operad by what? So they are some intersection, and they are also some marked points. So the thing which I have drawn may belong to, let's say, M4. I am ignoring the genus because I may of course think also of some close intersections and so on, and the components may have their own genera. And if I have another curve, okay, I'll draw a different color. The opera decomposition is defined by introducing another normal intersection by join the marked point. So for instance, if I wish to say what M2, 3 is, so sorry, circle 1 to circle 2, 3 is, I take point labeled by 2, marked point labeled by 2 on the first curve, on the white one, and marked point labeled 3 on the red curve, and I join them, introducing normal intersection. Do you think it's adequate explanation, Ike? I cannot hear you.
Thank you.
So of course there is a kind of another version, like paste in surfaces around the punctures with parameterized boundaries. But although it's kind of more intuitive than this, to say precisely what we are doing, it's kind of nasty, and it's not so nice as this one.
That's actually what I had expected you to do, but this is okay.
Well, I don't want to talk too long. I can tell.
No.
Yeah.
Is there any other question or comment?
Yes, I have a question. I was thinking, when I think of operads, I think of them as encoding operations. So you kind of have a natural canonical endomorphism operads. I know the one for operads and props. Do you have for these other structures also as a canonical?
For operatic categories, if you mean, yeah, I do.
Yeah,
we do. And there is again, let me be somehow more detailed. That we can do it even for duoidal categories, let's say. So, which is very important in case of Markl's Batanian opera. He did it for n global categories. So we can have endomorphism opera which live in more general categories than just symmetric monoidal. And namely in Batanian's theory, it's very important.
Yes. I have a follow-up question maybe then. In the modular case, what kind of algebras do you envisage to encode using modulars that do not really work with the prop or operad case?
Yeah, I think that the idea of, or the purpose of modular operads is not to study algebras, but rather to describe combinatorial structure of some geometric objects, like the various families of surfaces and so on. And by the way, there is a very deep application of the theory in knot theory also. So they showed up. There is something which is called modulo envelope or modulo completion, which takes you from cyclic operads to modular operads. It's a very non-trivial thing which has a lot of application in combinatorics and geometry and knot theory. So somehow the modular operads are objects that live by themselves. Say what algebra is.
If I may add something, Martin, there is a crucial point between algebras modeled by modular operad and props that you know, is that for modular operads, you need a pairing, a non-degenerate.
Well, it need to be non-degenerate, but you have to have a pairing. Yeah.
Anyway, you need a pairing, and so your vector space has to be finite dimensional. And if you want to get rid of that, you need to specify who's the input, who's the output. You see? So this is the crucial point. Props allow you to say what are the inputs, what are the outputs, and so it can be applied to any infinite dimensional vector spaces.
Mm-hmm.
If you
I would say that another application of modular operads is this string field theory business, where everything sits on Hilbert space. So you have pairing for Hilbert spaces, so you have topology. But well, if you are just in combinatorics, you need something about dimension. Right?
Okay, thanks.
Is there any other question, comment?
Martin, which of those variants of operads that you described are associated with monads? Oh, we cannot hear you.
I think there's a problem with your microphone. Before you were answering and we could not hear clearly, and now we cannot hear you anymore. We can't hear you, Martin. I propose that we stop here. I mean, yes, in the blue space, the microphone works. So for the Zoom, there is a blue space where the microphone works. And if this guy is in the blue space, well, anyway, Martin, I'm sorry. I think we're going to stop here. But I hope you can hear us. We would like to thank you once again for this very clear and nice talk. And thank you very much. And I want to say to all of you that Martin's been very kind and he gave a very thorough survey, but he didn't present much of its new results. So I strongly advise you to come back at 3:30. You'll have a talk by Jovana Obradovic, and she's going to talk about a joint work with Martin and Misha Batanin on a minimum model of graph of operatic categories. So I strongly encourage you to come. And then after, you'll have two beautiful talks by Manuel Rivera and Daniel Berwick-Evans. And the first one is going to be very operatic too. So you're going to see that. So thank you very much for attending this morning. We're going to close here now. And let's meet at 3:30 this afternoon. So have a good lunch.
See you later.
Bon appétit, comme on dit.
Bon appétit.
Ciao.
See you later.